another settlement cases about Kansas International Airport. And another cases, for example, earth dam failure when the flood can maybe it's due to the erosion of the dam. And we discussed some cases about snow and its complications. For example, the large landslides in Porcelain Road, Hong Kong. Some high building destroyed in the landslide. From these cases, we know the soil mechanics aimed to solve the strength, the bearing capacity of foundation related with the strength, the shear strength of the soil, and the deformation. And the settlement of foundation due to the deformation of the underlying soil, okay? And the stability, maybe landslides due to the stability of snow, okay? But how to solve this problem? The solution of soil engineering problem, we need to know some about soil mechanics. It's fundamental to solve the problem. And others about geology, exploration, or experience. In civil engineering, experience is very important. Maybe one have no knowledge about civil engineering, but he has experience, so he can solve some problem. Yes. And economic. If we pay more for the civil engineering, we can solve many problems. But here, we should consider the cost of the civil engineering. So, we combine the soil mechanics, geology, exploration, experience, and economics to form engineering judgment. What engineering judgment? It's in our mind, but it's produced by the knowledge or experience or the exploration material or information, okay? For example, if we design a rock snow, how to determine the snow? If we design a rock snow, we should to conduct geological exploration and use soil mechanics for rock, for various kind of rock, due to its varying action or varying degree. We can determine or give the snow. Maybe the ratio of 1 to 0.2. But for snow of soil snow, maybe we should use ratio of 1 to 1 or 1 to 1.5. Okay, so this engineering judgment, so maybe complicated, but it comes from our knowledge, our experience. Okay. Next, we'll introduce our class. The content of our class, but the soil compilation, index properties, and soil classification. Maybe this is chapter 1, physical properties and engineering classification of soil. And then we'll discuss behavior of cohesive clay, seepage, coefficient of permeability, and stress, unsealing ground, or deformation, or compressibility of soil and sediment analysis, and the shear strain. Maybe these are fundamental principles of the soil mechanics. Use the principle of soil mechanics, we can solve some questions. Maybe natural earth pressure calculation, or determine natural earth pressure, and design returning wall, or no stability to attribute the stability of snow. How to attribute the snow stability, okay? And the bio capacity for the transcolor green elevator, the foundation failure due to the biocapacity is not satisfied the superstructure. Okay, so we should to know how to determine the biocapacity of the foundation. The for the soil mechanics, the content of soil mechanics. Okay? Next, we'll begin chapter 1. Physical properties of soil and the engineering classification. In these chapters, we'll give a description of assemblage of particles, a detailed explanation and a quantitative description of the soil characteristics. Okay. First, well, discuss the formation of soil. What soil? And you tell me what soil? You have the geology, okay? Okay. Maybe the soil is the product of rock weathering from the geology, okay? And the soil is an assemblage of particles, maybe it's catalyst. Okay, and the soil is three-phase system of solid, liquid, and gas or vapor. Okay. Here, we know soil come from rock. What soil? You know the rock, about rock, how it deposits or exists in our earth. Maybe it deposits in the surface of the earth. Okay, here now the earth have three parts, maybe the inner with the core or here maybe mantle. Okay. And the out maybe crust. Okay. And rock is the combination of crust and the upper mantle. Okay. So the earth composed with rock. changed to the soil. Maybe the rock is solid. It maybe how to it change to us deposit or calculate source.
When
Maybe.
you crash
to the due to the battery. Okay. Okay. About battery. Battery action. You know some type of battery action, maybe physical battery or chemical battery, and biological battery, okay, from geology, okay. And what battery action? It may be due to the solar radiation or atmosphere or wind or rain, more factors, okay? But for physical battery, our textbook, you can read the textbook page 1. The physical battery may be denoted by the action of wind, frost, rain, or snow, or the action of various force by the impact of wave and earthquake, or the variation of temperature and the freezing and the thawing in the rock. Okay? These actions may change the shape or the size of the rock, but it doesn't change the mineral composition of the rock. Okay? So we call original mineral when the mineral come from physical battery. You know more about the original mineral. Okay? Maybe some chord as fast like this. You know, or as fast and this grass, these are original mineral, okay, come from physical valuing action. And another type of valuing action we call chemical valuing. What chemical valuing? In our textbook, chemical process results in changes in the mineral form of the parent rock due to the action of oxygen, carbon dioxide, and water. When the soil in the atmosphere due to the water or oxygen or carbon dioxide, as the rock may be changed to another material. Okay, some new minerals will produce. For example, clay, minerals. There are 3 types clay minerals. Here in our textbook, page 4. Coordinate, elect, monoclinate, with the mainly 3 clay minerals. Okay. Except the physical valuing and the chemical valuing and biological. Biological valuing is also important. What's biological valuing? Now some soils have organic matter. Maybe the organic matter comes from biological valuing. Okay? And the humus or pig. Humus or pig. Organic matter. It comes from biological valuing. Okay. So from the formation of soil, we can obtain a conclusion. Maybe the source include soil particle, okay, or soil grain, and water in pool or gas formation of soil. For soil particles, there are inorganic mineral, okay? And organic matter. Okay. And water in all matters is two kind of water in all, maybe absorb water or free waters. Okay. From here we call soil is a three-phase system of solid, liquid, and vapor or gas. Okay. Next, we'll discuss the phase relationship. What phase relationship? Maybe the relationship of solid or liquid and vapor. How to study the phase relationship? Maybe soil is a complicated system. So when we study the question, we consider an element from the soil. We get element. For element of natural source, here soil particle, and here spores. Okay, maybe water or gas. But the soil particle and the water impulse or gas impulse distributed carefully. But for studies, we establish a figure like this. We accumulate the soil particle together to take its mass and value.
I see.
And
I see.
for water in pore,
Sure.
okay?
Yeah.
For breath.
Yeah.
Inorganic minerals classified to original mineral and secondary mineral. Okay. Original mineral come from physical boundary action of law. Secondary mineral come from chemical boundary action. Okay, and organic matters come from biological boundary action. This for soil particles. And among soil particles, there are some pores which fill with water and gas. Okay. Next, we'll learn how to evaluate the soil physical properties. Use the phase relationship. For elements of real or natural source, maybe the soil particle, water in pore or gas in pore, distributed carefully. Okay. But when we study the question, we put the soil particle together to take the mass and the value, and put the water together and gas together. So we separated the three phases in the figure. Here's value on the right and the mass on the left. Okay. Here's the subscript A W S mean R water and soil grade. Okay. So MA means mass of air. W means mass of water. S means mass of soil grade. And V A means volume of air. V W means volume of water. And V S means volume of soil grade. And here, volume of air and volume of water we call V volume of void. Okay. And next, from the cap map of three phases, we can give the parameters of every phase, the mass and the value of every phase.
Please, the VV, what other products made?
Yeah.
The VV, volume of A and
V at
V.
V means value of void.
Void.
Yes, void. Maybe the void filled with water and air. Okay. Usually, the mass of air equals 0, maybe very small, or we can negate the mass of air. Okay. Next, from the cap map, we can obtain some relationship about value, weight, and the specific gravity. Okay? So we can know some parameter about value. Porosity. Here's porosity. Means we divided by V. The value of void divided by the value of the soul. And the void ratio. V divided by Vs, the two parameters maybe here is different, okay? And the degree of saturation, where you VW divided VV is described the degree of water filled with void. Okay. And some parameter about weight. Water contained. We use W. It means mass of water divided by mass of salt grain, not mass of salt. Here, MS, not M. Okay? And some specific gravity for mass, maybe the specific gravity means gamma divided by gamma 0. Gamma means unit weight of soul. here gamma means weight of soul divided by value of soul, okay? And gamma zero means the unit weight of water. And here water specific gravity. And solid specific gravity.
Gotcha. What are the gamma represents?
Here,
Gamma.
gamma,
What?
yes, it means unit weight.
Unit weight.
Yes, unit weight of soul. Here, the solid specific gravity may be very important for the phase relationship. Here, may be useful to describe the phase relationship. Okay? And some unit weight total, or we call bulk unit weight. And solid or soul particle unit weight. And here, for dry souls, no water, only soul particle and air, because dry souls. And the unit weight means Ws divided by V, one value. Here, the question you can think: for soul submerged into the water level, what the total unit weight, or for this soul submerged into water, what the unit weight? Yes, we have the unit weight for saturated source, or effective or beyond unit weight. Okay. Next, we'll analyze the net parameter or net atom. Here, there are 9 ways of value. V, Vs, Vw, and Ms, Mw, Ma, maybe 9 atom, okay? From the relationship of mass and value, we can plug here M equal MS plus MW plus MA. Okay, MA here equal 0. So M equal MS MW. Okay, and MW, we can use the equation, maybe the density of water as the volume of water. Okay, here density of water is known, so we can use the volume of water to determine the mass of water. Okay, and volume, the relationship of volume here okay, volume of soil grain as volume of void, and okay, use the soil particle water as volume. Okay, really together the volume of soil. And here, my weight or value, if we know 3 of them or 3 of independent variable, 3 variable independent, but independent variables, maybe we as and we may be independent, okay? But we not independent. It equals the two the yes. If we know 3 independent variables, we can get others. And for saturated soils, maybe the VA equal 0, no R. So if we know 2 independent variables, we can get others, okay? But which weight or value is known in factors? Some parameters determined by laboratory tasks. From the laboratory parameters, we can get other indexes, okay? Next, we'll give the laboratory parameters and a method in the laboratory tasks. Okay. Measurable indexing net, bulk density solid density water content. For bulk density, it means log, maybe here's M, the mass of the soil, okay? Mass of the soil. Here maybe M, mass of the soil grain, and the mass of the water, okay? And its unit here is 2 units, and its typical value 1.6 to 2.2. And unit weight relative to the density. Unit weight equal density times the G, okay, gravtation. Okay, and its unit this. And how to measure or how to determine the bulk density in laboratory. Here from the photos, we use a cutting ring. You use the cutting ring, have you the cutting ring maybe a circular shape, have a certain head and a simplex, okay? We use the cutting ring to cutting a soil sample. Maybe the soil sample fell with the inner of the cutting ring, okay? And we measure the mass of the cutting ring. Maybe M1. And the mass of cutting ring with the soil sample, maybe M2. So we can get the bulk density, okay? Here's for cutting ring, the mass of cutting ring, and here for cutting ring and the saw. So M2 minus M1, maybe the soil mass, okay, mass of soil grain, mass of soil. So here mass of soil and divided by the value of cutting ring. Cutting ring have a certain value, okay? Maybe inner value 100 millimeter method this method used for laboratory tests, but in situ the method is not convenient. So some question, some method, sand replacement method or water replacement method used for situ unit weight of natural or compacted soil. Here's the question. You know how to use sand replacement method. What the sand replacement method or water replacement method? Okay. Here's the ground in situ, and we carry like this. A track like this, and we measure the weight of the salt, okay, and filled sand, filled with sand, and the mass of sand we can measure, we know. So the density of sand is known. Maybe the density of sand is we know. So we can write the value. The value, we use the mass of sand divided by the density of sand. Okay? And this value equal the value of salt. Maybe here, the value of salt equal the value of sand. So we use the value to determine the density of salt. Okay. Here's the sand replacement. And water replacement, similar to the sand replacement. We just fill water with the trap, okay? But when you fill with water, you should to place material to prevent the water into the soil particle. You should to here use water to prevent the water sinking. Okay, so here the two methods in situ tags. Okay. Maybe this method applicable for coarse grain soil. Maybe the size of grain is not convenient in laboratory. So we use sand replacement method or water replacement method. Okay. And another index, solid density. It means mass of soil grain divided by value of soil grain. Okay. These parameters depend on mineral, yes. And from the solid density, we can get corresponding indexes. Specific gravity, it means the density of soil grain divided by the density of water. Okay. And dimensionless, maybe ratio. So no unit. Okay. Have that? No?
Yeah, 6 minutes more.
Or 5? Okay, 5 minutes. From this value, we can maybe almost equal. Okay, so this value, the specific gravity, may be constant. We can use a constant value to calculate other parameters. Okay. And how to determine the solid density? Here we use parameters method. Okay. Use 100 kilometer put 15 as dry soil into it. And have you used the kilometer? You use now? And it's water like this. Water, okay. So when we measure the solid density, we get the bottle and the water, boiled water, filled with the water, and we measure the mass here, mass 1. And then we put the 15 dry soils into the bottle and fill with water. Maybe it's mass 2. So we can get the soil particle density. How to calculate this?
The mass of the sand and water in the bottle minus the whole mass of the bottle over the volume.
Okay, maybe here the mass of the soil, okay, the mass of the soil this, yes, but the value of the soil particle.
Actually, that one is different. The mass of the soil.
We can use the bottle filled with water, the mass, and the part thing, and the matter. Yes, matters. The bottle filled with the dry soil and the water. Okay. Yes. And from this mass, we can get the value. Maybe the water density is known. So we can write the solid density. Specific gravity of soil particle does not vary in a large range. Maybe these values we can 2.7. From here we can say maybe get a constant value. Okay. Okay, have a rest. Maybe the phase relationship is very important in the soil mechanics. Okay. From the cat map, we describe the air, water, and the soil map in the depth and value on the right. Okay. And some parameters related to the value, weight, unit weight, and specific gravity. Here, porosities, void ratio, degree of saturation, and water content, and the mass, specific gravity of water, specific gravity, and solid specific gravity, and unit weight related to the density of the gamma equals density density times gravity, okay? Next, we'll discuss the measuring method of the laboratory index. What laboratory index is 3 parameters: bulk density, solid density, and water content are measured in laboratory tests. Okay. We use the cutting rate to showing bulk density. Okay. Here, the cutting rate like this. The cutting a soil sample filled with the inner of the cutting rate and measure the cutting rate mass and the soil with cutting rate mass and the inner cutting rate value is known, maybe 100 cubic centimeters or 200 cubic centimeters. Okay, so we can obtain the bulk density. But for in situ tests, we should use sand replacement method or water replacement method. Here, sand replacement or water replacement aim to get the value of soil. For example, we carry a pig. Here, a pig here, and measure the mass of the soil. Get the mass and the mass of the shoe is known, but the value of the soil is determined by the sand or the water. But when we pour water here, we should allow a plastic film to prevent the water flow or water seepage. Okay, so use the water density or sand density, we can obtain the value of the soil. Here, the sand replacement method or water replacement method. And another index, solid density, or we call it density of soil particle. It means mass of soil grain divided by volume of soil grain. Okay. And corresponding index is specific gravity. Use the density of soil particle divided by the density of water. Okay. No really. Okay. And its value in the range of this maybe equal 2.7 gram per centimeters, okay? And we use a meter method to determine the solid density. Okay. And the water content means the mass of water divided by mass of soil grain. Okay. If it range from 0 to 14% for clay, or 20% to 60% for sandy soil. Here, the water content may more than uric. And it suitable method open. This method applicable for clay, soil, and sand. This method may be simple. We get clay 15 to 16 gram, sand or organic soil 15 gram into the oven. Maybe temperature control 105 or 110. For clay, maybe the time 8 hours. For sand, maybe time at least 6 hours. And the clay, we use a box like this. As a cover, okay? Put the soil in a box and cover it. And first, we measure the mass of box and the soil and the ball. The ball mass, we use mass 1. The mass of ball with soil sample, we use mass 2. Okay? And in the oven for some time. Okay? And then we take it out and we show it the mass 3, okay? And the water content, how to calculate. And here, mass of water, we use M2 minus M3, okay? And here, the mass of soil grain, we use M3 minus M1, okay?
Yeah.
the water content. From the three parameters in laboratory tasks, we can get other indexes. Here, watt ratio or porosity. Watt ratio and porosity is used to evaluate the condition of soils. Maybe it's loose or it's dense. Okay, use the watt ratio or porosity. And its relationship. The porosity equals watt ratio divided by 1. Watt ratio. How to get the equation from the figures? If we assume the value of soil grain equal unit 1, and the value of void equal E, watt ratio. Okay, here's 1. Maybe value of void equal E. So the total value equals 1 plus watt ratio E. Okay. So the porosity equal the watt value divided by the total value. Okay. For sandy soil, maybe the porosity at rate 28% to 35%. For clay, 13 to 15%. Sometimes up to 16 to 17%. Maybe for 16 to 17% soil, it's very loose. Okay. And water content, degree of saturation, the two parameters to describe the moisture of the soil. Maybe the soil is wet or is dry. Okay. Here, degree of saturation characterize the degree of water filling in the soil void. When the degree of saturation equal 0, maybe the soil is dry soil, no water, only soil particle and the air. All the air filled with the soil void. But if the degree of saturation equal 1, maybe saturated soil. no air. The soil void filled with water. Okay? But in natural, the soil almost unsaturated soils. Maybe the degree of saturation between 0 and 1. Okay? And some parameters related to density and unit weight. Here we have varying density or unit weight in various conditions. Maybe bulk density or dry density or saturated soil density or effective unit weight. What the difference between saturated soil unit weight and effective unit weight? What the difference? The two parameters describe the soil submerging into the water, maybe below the water level. We use saturated soil unit weight or effective unit weight. In relationship, the effective unit weight equals saturated unit weight minus the water unit weight. Okay? How to derive this equation? Now, here, effective unit weight to consider the beyond force of the water. Okay? So we can write the equation. Here, mass of soil grain minus of volume of void for saturated soil, volume of water. Okay? Here's the arm force of the water. Here, like this, give the effective unit weight. And saturated unit weight as here the weight of soil grain, here the weight of water, okay? And equals weight. So we use the saturated unit weight minus unit weight of water, and here like this, okay? Here we can change the equation. V minus VW, maybe V as okay, maybe it's equation. So next we have comparison of indexing. Maybe the densities, bulk density, dry density, saturated soil density, which is bigger? Which is biggest?
Saturated soil density.
Yeah, the saturated soil density is biggest.
Yes.
And the bulk density between the saturated density and dry density. And dry density is the
least.
yes, most. How you derive the conclusion? From the definition of the parameters and the relationship of phase to give explanation. Can you give me an explanation why the saturated soil density is the biggest? When we compare two of the indexing, okay, maybe the dry density divided by value, and the bulk density R divided by value. Okay, M as no more than M. So maybe the dry density less than the bulk density. Okay. But saturated density with the bulk density, how to compare? Why you know the saturated density more than the bulk density?
Saturated density is used
Here, as
density of water
okay,
value
and
more
all equal
mass over
as
volume.
here. Here. We W less than we void, one void, okay? So the saturated soil density more than bulk density. And the unit weight, the relationship of unit weight here. You can use the same method to give the explanation, okay? Maybe of wealth, this equation we can obtain from the density comparison, okay? But with the effective unit weight, why the dry unit weight more than effective unit weight? Okay. Why? The dry unit weight, we use the weight of soil grain divided by value. But for the effective unit weight, we use the weight of soil grain minus the force of the soil grain. It means V as times K here W is here Ws minus Vs times gamma W. So with the dry unit weight more than effective unit weight, okay? When we study the phase relationship, we can assume one of the atom equal unit, maybe Vs equal 1. Why we can make the assumption? But the parameters or the ratio of mass to mass or mass to value or value to value. So we can assume the Vs equal 1. Okay? We have a question for you. If we know the laboratory parameters like bulk density, the density of soil particles, and water content, maybe the 3 parameters is given. How to calculate the porosity, water ratio, or saturation, degree of saturation, or density. Okay. How to determine other parameter? Here, we know the 3 parameters. Now to calculate others. How to do?
To do with this
Yes, we assume the
Vs equals
one of software equal unity, and here maybe water content or density of soil particle or density of bulk density is known, is given. We can use the relationship of the definition to give the atom. Okay. Here, Ma equal 0. And W. Here, we can use from this equation, we can obtain the mass of water equal water contained times Ms, okay? And Ms, we use the density of soil particle. Ms divided by Vs, Vs equal 1. Really. So, maybe the Ms equal log S, okay? So here, W equals log S, like this. Here, the result, okay? And Ms equal log S. Or we can use the unit weight, okay? And the value of the value of water. Here we use the mass of water divided by unit weight of water, okay? And here, void, value of void equal
E. So y is equal to E.
Here Vs equal 1. Void
E.
equal E, okay? And void, the value of water equal this equation. So from the scale figures, we can get the relationship between three-phase induction. Okay. Maybe you cannot take the equation in your mind, maybe more and complicated. But if you grab the method, you can do the calculation, okay?
Okay.
Now, here, example, in our textbook, example, three, okay, and page 29. The value of a source basement is 16 centimeters, and its mass is 108 grams. After being dried, the mass of the sample is 96.43 grams. The value of GS is 2.7. Calculate gas density, dry density, saturated density, contain, porosity, and the degree of saturation. How to do the program? If you may have some time to think it, okay? I have that. Not, okay? Here the MS well, and the GS
2.7.
here the
2.7.
condition is Hamilton we know. Now we should the wet density with off density and dry density, saturated density, water content, porosity,
Figure saturation.
and saturated degree of saturation. Here we should calculate the parameters. Maybe the vast density is simple.
Mass
Use
of
the mass of the specimen divided by the
volume.
width value of specimen. Okay.
Yes.
And the water content, use the
Mass of the
MS and W equals and minus MS. Okay, so the water content can obtain. And that's
dry density.
we calculate the dry density, the MS divided by
Feet.
V. Okay. And here, porosity or degree of saturation or the saturated density. How to calculate? Here the relationship of mass and another we should determine the relationship of volume. Okay. Here volume of water. Use the volume of use mass of water divided density of water. Okay, the density of water is known. And value, the total value is given. Okay, so we can Oh, and Vs, how to determine the Vs? We use the MS divided by the density of soil particle. And noise, use the GS to calculate noise. Okay? GS equal noise divided by the density of water. So we use the here GS and more W. So Vs can determine and the total we know, and we can get the volume of void. Okay? Like this. And the volume of void, no. The volume of water, no. And the volume of air. Okay? So, the quantity equals V divided by V. Here we know. And degree of saturation, VW divided by VW, you know, VV, no. And saturated density, where you this equation, okay? As the we have no W divided by V. Okay? Here, no. Okay? So you can get the textbook, get the results of the timing of the classroom. Okay. Maybe example 1.4 is difficult. Yes, maybe it's complicated or difficult. A source basement has a water content of 12% and the unit weight of 19 kN cubic meter. Keep void ratio constant and increase water content to 22%. How much water will be infused into 1 cubic meter soil? This question is very maybe useful in the civil engineering. Sometimes in heavy engineering, we should to fill the embankment and according to the contain with the we should use the water content 22%, but now we have the soil material. Water content 12%. So we should add water. Okay? How to calculate the water? We should infuse in the soil. Here, the void ratio may be a constant. Void ratio means no matter we add water, the void ratio may be a constant. Okay? How to do the problem? One method, we can take the unit weight before increase water and after increase water. Okay, the relationship between the unit weight. Okay, so we use the void ratio with constant. Here is equation every this equation from the relationship here. Here, E1. And GS is a constant. And the density of water is a constant. Before increase water, the water content may be 12%, okay? And the unit weight maybe unit weight 1. Here equals okay, and after increase water, here raise and E equal E2. So here can that and this can this equation is obtained. Here, no, and we can obtain the unit weight of gamma 2. But the question is to calculate the water mass how to calculate the water mass. If that's right?
Yes.
Yes. Okay. When the mass of soil grain is constant, so the decrease of the unit weight due to the increased water mass. Use the equation. Another method, we can use the dry unit weight. Dry unit weight. Dry unit water content W1 is 12%. We can calculate the dry unit weight. use the unit weight 19. And here's 12%. And the down equal 16.96. Here, different gamma with gamma D. What's the difference? Maybe the difference describe the water mass. Okay. So here water mass we can use the gamma 1 minus gamma D1. Okay. Gamma 2 not WW2 equal WW1. That's right?
Yeah.
Okay. So use this equation, we can obtain the weight of water when we increase the water. When the water contains 22%. Okay. So how many waters we should infuse? How many water? WW2 minus WW1. Okay. In the page of 15, at page of 15, here's some exercise. 50. Okay. Here, homework. Exercise 1, 2. 1, 4, or 1, 5, maybe for additional homework. You can do it or you not do it. Doesn't matter, okay? But 1, 2, 1, 3, you should do it. Okay. Now let's have a summary. Here's some emphasis, the phase indexing. You should know the definition of the phase indexing. Maybe 9, there are 9 indexes. You should know the definition, okay? How to define the phase indexes. And then you should know the 3 parameters come from laboratory tests measured in tests. What parameters? Bulk density, the density of soil particle, and the water content, the 3 parameters. Okay, and the other density, how to calculate other density, other index. Here, some useful tools. First, draw a step map, okay, or assume the Vs equal 1, okay, and give the mass of soil particle, water or gas, value of soil grain, water, and the void or gas, and then use the definition of phase indexes. We can obtain the index. Okay.
Okay.
It contains maybe very important, maybe aspect of our soil mechanics, especially physical property of soil. Okay. This indexes is used to describe physical property of soil quantity. Okay. Okay, next we should to discuss particle size distribution. We know soil particles varies in size and shape. Maybe the shape of particle is irregular, okay? So it is meaningless to study the size of a certain particle. But the mass distribution of soil particles of different size is very important. So we should know the particle size distribution, not particle size. Okay? Here, what factors affect the particle size? You know what factors? The main influence factors.
Maybe not in the water,
Uh,
maybe weather,
what?
weather.
One way. Okay. Maybe the original minerals or secondary minerals or the transportation
Yeah.
of flood, wind, or glacier. Okay, that's the main influence factors. Okay. And how to describe the particle size distribution? Maybe the proportion of particle in each size. But we know the particle, the soil particle varies in size. So we should give a group of particles. Here we suggest group of particles. What group of particles? Particles group by size. In this figure, we can say the fine grain soil or coarse grain soil and grain soil. And the diameter less than 0.075. You have 5 grain soils. Diameter more than 60 millimeters per use grain soil, okay, and others called coarse grain soil, okay, and we can classify in pebble or gravel, sand, lead, clay, okay. And when we study the particle size distribution, we should use measurement method or tax. We call it particle size tax. How to do a particle size tax? Here, use this C method. to separate the various size soil particle. Okay, you save method. Or we use the sinking task. Okay. Sinking tasks applicable for fine grain for the fine grain soil, maybe diameter no more than 0.075. We use sinking tags. Diameter more than this, we use sieve method. Okay. So we use the tags in laboratory. We can separate the group of particles, the mass of group of particles. Okay. For example, if the total mass 15 grams and the answer more than is maybe 5 grams or the 2 millimeters, maybe 10 grams or 2 to 20, maybe 12 grams, maybe the 20 to 16, maybe 8 grams, and the 16